definition of DC circuit. What is a DC circuit? There are actually two types of circuits. There are two types of circuits in physics. Number one is called the open circuit. Number two is called the closed circuit. There are two types of circuits in physics. Number one is called the open circuit. Number two is called the closed circuit. Alright. Now, what is an open circuit? An open circuit is a circuit where there is no flow of current. It means the power source has been disconnected. An open circuit is a type of circuit where there is no flow of current. There is no flow of current. It means the switch is off or is open. That's what we call an open circuit. Take for example, if there's a switch here that's linked, that is connected to all the bulbs here. If you put off that switch, alright, you'll find out that the light will go off. Now when you put off a switch, it is called an open circuit. But when you switch it on, it is called a closed what? Circuit. So an open circuit, there is no flow of current, alright? An open circuit, there is no flow of current, but a closed circuit, there is what? Flow of current. It means there is potential difference and current in closed circuit. But in an open circuit, there is no current and no potential difference. Alright? So that is that for the two types of circuits. So let's begin the class proper. What is a DC circuit? By definition, a DC circuit, this word DC, it means direct current. This word DC, it means direct current. So DC circuit is a direct current what? Circuit. A direct current circuit is a circuit in which the flow of current is unidirectional. A DC circuit is a type of circuit in which the flow of current is unidirectional. What does it mean to be unidirectional in the flow of current? It means the flow of current is always in one direction. I said a DC circuit is a type of circuit in which the flow of current is what? Unidirectional. Unidirectional means the flow of current in that particular circuit is what? In one direction. Are we following? A DC circuit comprises of three basic electrical devices. Number one, resistor. Number two, a switch. And number three, a battery. A DC circuit is composed of three major electrical devices. Number one, resistor. Number two, switch. Number three, a battery. Are we following? Now, this is that for DC circuit. Let's look at a sketch. Let's sketch a typical DC circuit. Let's sketch a typical DC circuit. We said DC circuit is composed of resistor, it's composed of switch, and it's composed of what? Battery. Please listen attentively. In a DC circuit, you can only find resistors. In a DC circuit, you only find what? Resistors. Whenever you find resistor, capacitor, inductor, rectifiers, transformers in a resistor, in a particular circuit, whenever you find every other device, resistor, capacitor, inductor, amplifiers, transformers, in a particular circuit, it is more likely to be an AC circuit. Alright? So what is an AC circuit? If there is DC, there is AC. We are going to compare the both of them. Alright? We said DC circuit, flow of current is, in DC circuit is what? Unidirectional. But in AC means alternating what? Current. If DC is direct current, AC is alternating current. It means the flow of current in an AC circuit is reversible. It means the flow of current moves forward and backward. I'm going to explain. Right? The flow of current in an AC circuit is not unidirectional. It is reversible in an AC circuit. Now let's take a typical example of a DC circuit. We said DC circuit comprises of three electrical what? Devices. Number one, resistor. Number two, what? Number three, battery. Now, let's get a typical DC circuit. A typical DC circuit is composed of a resistor. This is the sign for a resistor. If you want to draw the symbol for a resistor, it's either, observe, a line. If you start up, you end down. I started up, I ended where? Down. If you start up like this and you end up, it means another electrical device. If you start up and end up, it means another electrical device, and that is called an inductor. But if you start up and end down, it is called a what? Resistor. If you know this one is going to be too difficult for you, use the box to represent the resistor. It's either you use this to represent the resistor or you use this to represent the resistor. But this is not the symbol for a what? Resistor. Are you following? Please, if you have questions, Ask questions. Don't just look. If you're not following, ask questions. Alright? So, a typical DC circuit is composed of a resistor. Let's call this R1. It's connected to a switch. This is the switch. It's connected to a switch. And to a battery. This is it. This is it. Look at, in a battery, the longest terminal is positive. The shorter one is what? Negative. This is the battery. This one here is the switch. And this one is called what? Resistor. Now please, listen attentively. Alright? Resistance of a resistor is measured in ohms. Resistance of a resistor is measured in what? Ohms. OHMS. Resistance of a resistor is measured in what? Ohms. The symbol is this. This is the symbol for ohms. Resistance of a resistor is measured in what? Ohms. Please take note. Alright, so let's call the resistance of this resistor to be, let's say this is 3 ohms. Alright? Let's call the resistance of this resistor, let's say it's 3 ohms. Now I want to explain something. Please listen up, listen up, listen up. In the study of electrostatics, we said that currents or electric charges, they move from what terminal to what terminal? Positive to where? Negative. They emanate from positive and they terminate where? Negative. If we said that the supply of this battery, let's say this is 3 volts. Let's say this battery is 3 volts. The potential difference of this battery is 3 volts. This battery, when you connect it to a resistor and a switch, if the switch is like this, it is open. When the switch is like this, it is open. But when it is like this, it is what? Closed. Now when it is closed, there is supply of what? Current. But when it is open, there is no what? Current. Are you following? Now when the switch is closed and I connect it to a battery, you'll find out that this battery is going to supply current. This current is going to move from the positive in this direction, it will go in this direction, it will come to this direction. Now if this battery is supplying a current of 3 ampere, please listen attentively. This is going to help you in understanding Kirchhoff's voltage and current law. This battery, the current is moving from the positive terminal like this. Let's say this battery is, I'm just assuming, let's assume that this battery is supplying a current of 3 ampere. The unit of current is ampere. If this battery is supplying a current of 3 ampere, this resistor, the function of a resistor is to oppose the flow of what? Current. Now what does this resistor do? This resistor would oppose the flow of this 3 ampere. It means that 3 ampere of this current that is coming from this battery is 3 ampere. When it comes across this resistor, not all the current will pass. Since the function of a resistor is to oppose the flow of what? Current. It means about, let's say 1.5 ampere will pass. The function of a resistor, it opposes the flow of what? Current. So the more resistor you put, the more opposition of the flow of what? Current. If this battery is supplying a current of 3 ampere, not all the 3 amperes will pass. Because there's a what? Resistor. Resistor will allow some to pass and prevent some not to what? Pass. That is where the name comes from. Resistor. It opposes the flow of what? Current. Now when 1 ampere, 1.5 ampere passes through this resistor, it just goes this way and it comes back to the negative terminal of the battery. You can also put an LED like a bulb. If you put an LED like a bulb, the reason why you see some, you know what's called an LED? Like anything diode, all these mini bulbs, all these small bulbs, it can be red, it can be blue, it can be white, it can be any color. The reason why when you connect those bulbs to any circuit and they don't blow is because the battery is supplying a voltage or a current of 3 ampere. Not all 3 amperes goes to light up that particular bulb. Because there's a what? Resistor. The resistor has prevented. If there's no resistor here, somebody might ask, if there's no resistor here, what will happen to this circuit? If there's no resistor here, and I place a bulb, let's say I place a bulb, a light emitting diode, I place a bulb here. If there's no resistor, what is going to happen? If the capacity or the potential difference or the current that which this bulb can take is not up to 3 ampere, this bulb would explode, it will just blow. You've seen some certain scenarios like that. It will just blow because there's no what? Resistor. Now the reason why they put resistor is so that it's going to prevent some current from passing to the bulb or coming back to the battery. Resistor prevents the flow of current. It means it allows some and it prevents what? Some. That's the essence or the reason why you put resistors in what? Circuits. Any question? Current, we say, flows from where to where? Positive to negative. And when it comes across a resistor, what does the resistor do? it opposes. It means a certain percentage of the current will pass and the other should be what? Prevented. Just have that understanding. It's going to help you a lot. Alright? Just have that understanding. So we said in a DC circuit, we have a resistor, we have a what? Switch, and we have a what? Battery. Now let's compare it to an AC circuit. Let's compare it to an AC circuit. An AC circuit is composed of 4 major components. An AC circuit is composed of resistor, inductor, capacitor, and AC generator. An AC circuit is composed of 4 major components. An AC circuit is composed of 4 major components. Number 1 is called a resistor. Number 2, a capacitor. Number 3, an inductor. And number 4, an AC generator. Or you can call it an AC supply. Alright? An AC generator. Let's give a typical representation of an AC circuit. We said it's connected to a resistor, a capacitor, and an inductor. Look at this. This is capacitor, inductor. Look at this. This is an AC circuit. AC circuit is composed of resistor, capacitor, inductor. This is the symbol for capacitor. Capacitor is just like you're writing 11. 2 equal parallel lines. Alright? That's the symbol for a capacitor. This is the symbol for an inductor. And this is an AC supply. Or an AC generator. These are AC circuits. Alright? We said in an AC circuit, the flow of current can be forward or what? Backward. The flow of current is reversible in an AC circuit. It means that, what does it mean? It means that this AC supply, please listen, this AC supply supplies voltage. The unit of this AC supply is volts per hertz. This AC supply is in volts per hertz. It means that the supply of current in an AC can go forward like this, or it can go backward. Are you following? In an AC, the supply of current, look at this is an AC supply. AC supply, there is no positive, there is no what? Negative. So it means current can go this way, or current can go this way. But in a DC circuit, current must go from where to where? Positive to negative. It means current must go from this side, and if come across a resistor to oppose the flow of what? Current, and it will return back to the where? Negative. Who is lost? In an AC, we have resistor, capacitor, inductor, and an AC supply. We said the function of a resistor is to oppose the flow of what? Current. The function of capacitor is to store electric charge, and the function of an inductor is to induce electric current. The function of a resistor is to oppose the flow of current. Capacitor stores current as charge. Inductor induces the flow of current in an AC circuit. Inductor induces the flow of current in an AC circuit. When we talk about AC circuits, when we get to AC circuits, we'll look at something called impedance. We'll look at capacitance. We'll look at reactance. Alright? You can connect each of these components to an AC supply, connect capacitor to an AC supply, inductor to an AC supply. Okay? But our interest for today is what? DC. Now, if you are asked to give 5 differences between an AC and a DC circuit, from what we have on the board, can you do that? If you're asked to give 5 major differences between an AC and a DC circuit, with what we have on the board, can you do that? Number 1 difference between AC and DC. A DC circuit, the flow of current is what? Unidirectional, in one direction. In AC, flow of current is what? Is what? Reversible. That's one difference. Number 2 difference, look at us. Number 2 difference between AC and DC. From what you're seeing, in DC we have only what? Resistor, switch, and battery. In AC we have resistor, capacitor, inductor, and what? AC supply. Which are the difference between AC and DC? Boom! DC circuit flows from where? Positive to negative. In AC, it can be forward or what? Backward. Because there's no positive or negative terminal. Who can tell us another one last one? Between the difference between DC and AC. Who can tell us the difference between DC and AC? The name. DC is what? Direct current. AC is what? Alternating current. Very easy. So let's come back to what we're discussing. DC circuits. Alright? DC circuits. Let's start with a resistor. What is a resistor? Since we said DC is composed of resistor, battery, and switch. So what is a resistor? Let's start from there. Please, if you're drawing the symbol for a resistor, draw it correctly. What is a resistor? A resistor is an electrical device. Have I given the definition for a resistor? No. A resistor is an electrical device that opposes the flow of current in one direction. A resistor is an electrical device that opposes the flow of current in one direction in a DC circuit. A resistor is an electrical device that opposes the flow of current. An electrical device that opposes the flow of current in one direction in a DC circuit. It must be in one direction. Alright? That's what we call a resistor. The amount of current that is opposed by a resistor is called resistance. The amount of current that is opposed by a resistor is called resistance. Please take note. The amount of current that is opposed by a resistor is called what? Resistance. The unit of resistance is ohms. The amount of current that is opposed by a resistor is called what? Resistance. And the unit of resistance is what? Ohms. Are we following? The degree of opposition to the flow of current, please take note of the words I'm using. The degree of opposition to the flow of current, the degree to the opposition to the flow of current in a DC circuit is called resistivity. The degree to the opposition, please, what did I say? I'm using, I want to use another word now. The degree of opposition to the flow of current in a DC circuit is called what? Resistivity. If I say the degree of opposition or the degree of hindrance, the degree of opposition to the flow of current is called what? Resistivity. The symbol for resistivity is P, just like the unit for density. This is the unit for, this is symbol for resistivity. The unit for resistivity is ohm meter. The unit for resistivity is ohm meter. I said the degree to the opposition of current is called what? Resistivity. It means that resistivity is equal to resistance times area over length. Resistivity is resistance times area over length. Resistivity is resistance times area over what? Length. The unit of resistance is what? Ohms. The unit of area is meter squared. The unit of length is meter. At the end of the day, you get what? Ohm meter. Alright, so that is that. We've looked at resistors, definition, resistance, resistivity. Let's look at, I want to take it sequentially. Let's look at resistor combination. That is the most important aspect. Knowing how to reduce circuits, resistor combination. Resistor combination. Resistors can be combined in series or parallel. Some textbooks refer to it as resistors arrangements. Alright? Resistors can be combined in series or parallel. They can be arranged or combined in series or parallel. Now let's start with series arrangement of resistors. Series arrangement of resistors. I want you to get the important information because at the end of this class, you should be able to reduce a circuit and get or calculate the current across a particular resistor of resistance. Series arrangement. Series arrangement. Series arrangement of resistors is when resistors are connected end to end. When resistors are connected end to end, it is called series arrangement of resistors. When they are connected end to end, it is called a series arrangement. Let's take an example of series arrangement of resistors in a DC. Alright, so this is my battery. Let's say this is 3 volts. This is arrow 1, arrow 2, R3. Hope you know you can decide to use the box format. Whichever one is convenient for you, you can decide to use any one, whether the box format or this sinusoidal form. But if you start off, you must end well down. Alright, so let's consider this resistors arrangement in series. One thing you need to understand whenever resistors are in series is that they have the same current but different potential difference. Please take note, this is the most important thing in resistors in series. When resistors are arranged in series, they have the same current but different what? Potential difference. Another name for potential difference is called what? Voltage. Are you following? When resistors are arranged in series, they have the same what? Current but different potential difference. What do I mean? Is that, look at this. If the current supplied by this battery is 1.5 ampere, it means R1 will have 1.5 ampere, R2 will have 1.5 ampere, R3 will also have 1.5 watts ampere. The current across, please listen, I said current. The current across R1, R2, and R3 are going to be the same. The reason is because they are in what? Series. But their voltage, will it be the same? No. The voltage will vary in accordance to their resistance. The voltage would vary in accordance with their resistance. If this is 1 ohm, this is 3 ohm, this is 6 ohm, it means the voltage across 1 ohm will be higher compared to 2 ohms and that of what? 6 ohms. But their current is going to be what? The same. It means to calculate the equivalent resistance, or effective resistance of resistors in series, it is just the summation of the resistance of all the resistors. R1 plus R2 plus R3. If you have more, up to Rn. This is the formula used to calculate the equivalent resistance of resistors in series. Now let's look at resistors in parallel. Which aspects? Where? I said this formula is used to calculate equivalent resistance. Alright? Who's asking this one? Equivalent resistance, okay. Equivalent resistance means total resistance. What does it mean to get equivalent resistance? Equivalent resistance, let me explain to you in a layman's understanding. Equivalent resistance means this R1, R2, R3, they are working for this guy, the battery. I can remove R1, R2, and R3 and replace it with somebody that can serve the function of R1, R2, R3. I'm going to give you an example. Please listen. If I have the value of R1 to be 3 ohms, and I have R2 to be 5 ohms, and I have R3 to be 2 ohms, since they are in series, this is their resistance. 3 ohms for R1, 5 ohms for R2, 2 ohms for R3. These are their resistance. If I want to get the equivalent resistance of this particular circuit, it's going to be 3 plus 5 plus what? 2. And that is what? 10. Isn't it? It means I've reduced this circuit. Whenever you calculate equivalent resistance, you must use an arrow to show that the circuit has been reduced. It's a must. So that if I've got equivalent resistance, I'll have something like this. Connected to my battery. The battery is 3 volts. Alright? And I've got the equivalent resistance to be what? 10 volts. I've reduced this circuit to this. I've reduced this circuit to this. It means that instead of employing 3, 5, and 2 people to carry out their job or this function, I can just bring in just 10 ohms. 10 ohms can serve the function of 3, 5, and what? 2 ohms. This is the technique or the mechanism at which they use in making electrical devices. That's why you see that the circuits of your phones are very, very small and tiny. You just see 1 or 2 resistors. It's because that particular resistor can serve the function of so many resistors. What they just did, they got the equivalent resistance of the resistors in series and in parallel and gave them one value and they just put in that particular resistor. So the equivalent resistance of 3, 5 ohms and 2 ohms is what? 10 ohms. It means the current, please listen, since they are in series, they have the same words. They have the same words, current, but different words. Good. If they ask me now to get the current across R1, if I'm asked to get the current across R1, the current across R1, is it the same thing across R2 and R3? Yes. So what do? I will just get the current across the equivalent what? Resistance. Whenever you're asked to calculate the current across a particular resistor, you're interested in the equivalent what? Resistance, if they are in series. So if I want to get the current across R1 or R2 or R3, what I'll just do from Ohm's law, V is equal to IR. My current I is equal to V over what? R. My voltage is what? 3 volts. And total resistance is what? 10 ohms. What do I have? 0.3. 0.3 what? Ampere. If 0.3 ampere is flowing through 10 ohms, if 0.3 ampere current is flowing through 10 ohms, how did you get this 10 ohms? Is it not from adding 3, 5, and 2? It means that this 0.3 ampere will be flowing through R1, R2 and what? R3. Because they are in what? Series. Who is lost? Okay, let's look at resistors in parallel. Resistors in parallel. Yes, any question? Is there any question on this? Resistors in parallel. Resistors are said to be arranged in parallel if they are connected to a common terminal. Resistors are said to be connected in parallel, arranged in parallel if they are connected to a common terminal. But for series, if they are connected end to end. Let's take an example of resistors in parallel. If I have this, I said resistors are connected in parallel if resistors are arranged in parallel, they are connected from a common terminal. Let's say this is 3 volts, this is R1, R2, R3. Resistors in parallel, they are connected to a common terminal. This is the common terminal, this side. A common terminal. Give the common terminal. I'm going to, after this, I will explain how to identify, because when I give you a series of parallel connection of resistors, you might get confused. But I'm going to explain using another example, citing another example so you understand better. If resistors are connected in parallel, their equivalent resistance is 1 over R equivalent, and that is equal to 1 over R1 plus 1 over what? R2 plus 1 over what? R3 till you get to 1 over R1. This is the formula for resistors in parallel. Resistors in parallel. 1 over R1 plus 1 over R2 plus 1 over R3 till infinity, the number of resistors we have. Alright? Resistors in parallel have the same potential difference, the same voltage or potential difference, but different current. Have the same voltage or different current. Resistors in parallel have the same voltage but different current. Please take note of this. So take note of this. If I have R1, please listen up. If I have R1 to be 2 ohms, and I have R2 to be 3 ohms, and I have R3 to be 4 ohms. Alright? Let's say I have R3 to be 6 ohms. If I have something like this, R1 is 2 ohms, R2 is 3 ohms, R3 is 6 ohms. Let's calculate the equivalent resistance. Since they are connected in parallel, they have the same voltage but different what? Current. To get the equivalent resistance is 1 over what? R equivalent, which is 1 over what? What are R1? 2. 1 over 2 plus what? 1 over 3 plus what? 1 over 6. Now we solve this as a fraction. The LCM of 2, 3, and 6 is what? 6. My LCM is 6. 2 divided by 6 is going to give me what? 3. 3 times 1, 3. Plus 3 divided by 6, 2. 2 times 1, 2. Plus 6 divided by 6, 1. 1 times 1, 1. Isn't it? At the end, 3 plus 2 plus 1 is what? 6 over 6. It means that 1 over an rho equivalent is equal to 6 over what? 6. And that is 1. Please, I want to explain something. Let's just say, I think we added everything and we got 7 over 6. And just assume, let's just assume, because you see a calculation where you added, after adding everything, you got 7 and the denominator is 6, you have 7 over 6. It means that 1 over an rho equivalent is equal to 7 over what? 6. It means by taking reciprocal, an rho equivalent is equal to 6 over what? 7. This is how you get your final answer. Are we following? The one we brought was 6/6. 6/6, when I say 6/6, 6/6 still 1, isn't it? But if you have something like 7/6, let's assume we have 10/6. It means the equivalent is going to be what? 6/10. Are you following? Alright. Let's see how you can give a typical example on equivalent resistance. I'm going to solve one with you from the past question. You will solve the second aspect, the second one. The both of them are easy. So, question 1. Calculate the equivalent resistance and the current across calculate the equivalent resistance and the current across R1 and R4 in the circuit below. Calculate the equivalent resistance and the current across R1 and R4 in the circuit below. And the circuit below is let me know the circuit on the board. 5 points. Alright, so this is it. We're actually going to reduce this and get the equivalent resistance, get the current across. Is that R1 and R4? So we're looking for the current across R1 and R4. This was past question. Please draw the circuit so they can put it together. You can use the box to draw your resistor with the box symbol. Not the box you must use this one. I'm conversant with this conversion of drawing resistors. I'm conversant with this compared to the box type. So whichever one you want to use, you can use anyone. Alright. Okay, they said this battery is the voltage, the power source. Three volts. What type of circuit is it? Open or closed? Closed. The power supply, the battery is 3 volts. Alright, so are we ready? Alright, so let's start. Before, if you want to reduce, look at this. Let me give you a rectangle. You know what this is? I'm supposed to draw the wire like this. But in electricity physics, if you draw it like this, it's wrong. This sign I did means they are not connected. They are just crossing each other. You get it? But I just want to explain something. Just listen, this is R1. Let's call this R2. Let's call this R3. Let's call this R4. Okay, just look at this now. I want you to explain when you say something is in series and when something is in parallel. When you say something is in parallel, when something is in parallel or your resistor is in parallel, it is when it is connected from one terminal to the other terminal. Like it is in between. Look at this. R2 and R5 are in parallel. R2 and R5 are in what? Parallel. Because they are connected from one terminal to another what? Terminal. R5 is connected from one terminal to another terminal, like it's in between. If you assume this board could be a circuit. If resistors are connected at this point, and the last point, they are connected in series. Series is when the resistors are on the edges of the circuit. Do you understand? But if I draw something from here, if I place a resistor from here now, I place another resistor from here like this. I'm assuming this board to be the circuit. Let's say this resistor is connected from this point to this point. This particular resistor is in series or parallel? Parallel. But if this particular resistor now is placed here, or at the end, it is connected in what? Series. But whenever you connect a resistor from one point to another point, the resistor is in between. It is what? Parallel. That's the concept I want you to get. So let's reduce this. Alright, so how do we reduce a circuit? Please understand this. If you want to reduce a circuit, you start reducing the circuit, please listen, from the side directly opposite to the power source. if it's an open circuit, directly opposite to the open circuit. What do I mean? You start reducing the circuit from the engine. If I give you an open circuit like this is called an open circuit. This is called an open circuit. You know why it's called an open circuit? Because there's no what? Power source. This one is closed, isn't it? Yes. This one is closed because there's power source. This one is open because there's no what? Power source. Now, how do you start reducing? You start reducing the circuit from the last part. See, this is the part of the power source. The last part, or you can think it as the first part. This last part is where you start reducing. That means you take the last two. Are you following? You take the last two. When you get the last two, whether you series or parallel, you get the flare resistance. When you take the last two, you reduce it. You take this one, you reduce it. You take that one and this one, and last you take this one. If I want to start reducing this circuit now, will I start from arrow 5 and arrow 6? You start from the last. I'm calling the last or the first. Whichever one. You start from the last. It means I'm going to take which one and which one. Arrow 1 and what? Arrow 2. Arrow 1 and arrow 2 are they in series or parallel? Are they in series or parallel? Wait. Arrow 1, from what I explained here. No. Arrow 1 and arrow 2, are they in series or parallel? Series. See, I said, let me explain it again. This board is a circuit. If you have a resistor along this side, the edges, this side, and that last point, they are in what? Series. But if you have the connection from here to here, you have the resistor in between. Is in what? Parallel. So it means arrow 1 and arrow 2 are in what? Series. It means they will have the same what? Or different what? Voltage. Alright, so we'll start with, remember, if you're using a circuit, you start from the part that is directly opposite the power source. That is directly opposite the power source. Alright, so we start with arrow 1 and arrow 2. The equivalent since arrow 1 and arrow 2, I can make a statement. Since arrow 1 and arrow 2 are in what? Series. The equivalent resistance, it means arrow 1, 2, alright? Equivalent resistance for arrow 1 and arrow 2 is equal to, since they are in series, equivalent resistance without the summation, isn't it? It's going to be arrow 1 plus what? Arrow 2. And that is equal to 1 plus what? 5 ohms. And 1 plus 5 ohms is what? 6 ohms. So the equivalent resistance between arrow 1 and arrow 2 is equal to what? 6 ohms. I'm going to reduce this circuit. I've got the equivalent resistance between arrow 1 and arrow 2. Alright, I'm going to reduce it. You put your arrow, you reduce it, you withdraw this circuit again. It's a whole lot of work. So withdraw the circuit. So the one I'm going to give to you, I'm going to give you 15 minutes. And I'll go around and check. Alright, just sketch. You can sketch. This is 11 ohms. This is 3 ohms. This is 7 ohms. This one here is. No, this one, I'll do 12. 12 ohms. Now, the one we reduce between arrow 1 and arrow 2. The equivalent resistance for arrow 1 and arrow 2 give us what? 6 ohms. Look at the 6 ohms here. 6 ohms. Alright? As you reduce, you withdraw. As you reduce, you withdraw. This is what gives you mark. It is not this and the calculation. If I get the equivalent resistance now, for this one now, look at. You see that I started from the end. The last two. The end. Reducing this at the 6. Now observe. 6 and 12, are they in series or parallel? Parallel, thank you. They are in what? Parallel, because they are connected from one terminal to the what? Other. So 6 and 12 are in parallel. So if they are in parallel, to get the equivalent resistance, this 12 ohms is arrow 3, isn't it? This 12 ohms is arrow 3. This new equivalent resistance is the equivalent resistance between arrow 1 and what? Arrow 2. So to get the equivalent resistance, since I cannot say since arrow 3 and arrow 1, 2 are in what? Parallel. Equivalent resistance is going to be 1 over arrow equivalent is equal to 1 over what? 12. Isn't it? Plus 1 over what? 6. If they are parallel, their equivalent resistance is a fraction. Alright? 1 over 12 plus 1 over 6, but you can say 1 over 6 plus 1 over 12. LCM of 12 and 6 is what? 12. Alright, 12 divided 12, 1. 1 times 1, 1. Plus 6 divided 12, 2. 2 times 1, 2. 1 plus 2 over what? 12. Now, from this is 1 over array equivalent. Somebody should give me that equivalent resistance. Times 12 over 3 is what? 4. Is anybody lost here?
Yes.
Who is lost? Who is lost? Okay. At which what point? Here? Here. LCM of 12 and 6 is 12. LCM of 12 and 6 is 12. 12 divided 12, 1. 1 times this one, 1. 6 divided 12, 2. 2 times this one, 2. 1 plus 2, 3. So since you have 1 over array equivalent is equal to 3 over 12, it means if you take the reciprocal, array equivalent is equal to 12 over 3, and that is 4 watts. Boom. So we reduce this again, since it, you reduce. We reduce this. We reduce this. You just sketch. We reduce this. I've got the equivalent resistance between 12 and 6. It gave me 4. So here, this is 4 ohms. This one, 11 ohms. This one, 3 ohms. This one, 7 ohms. And this is 3 volts. 3 volts. Now, observe which one and which one are in series. 11 and what? 4. Are you seeing it? We took this and this to get 4. This 6 and 12 are in parallel to get 4. Now, this new equivalent resistance, 4 ohms and 11 ohms are in what? Series. So the equivalent resistance between this and this is just the summation. You can see you just add, isn't it? So it is 4 plus what? 11. 4 plus what? 11. And it's going to give us what? 15. So I can say since 11 ohms and 4 ohms are in series, it means the equivalent resistance is equal to 11 plus 4 ohms, and that is equal to 15 ohms. I will draw again. I'll have this. So this is 3 volts. This is 3 ohms. This one is 7 ohms, and I have this to be 15 ohms. Alright? So this and 11 gave me what? 15 ohms. Now observe 3 and 7. 3 and 7. The last is just this and this two, isn't it? But this 3 and 7, 3 ohms and 7 ohms are in what? Series. So if they are in series, the equivalent resistance between 3 and 7 is what? 10. Are you following me? Is anybody confused at this point? See, the last stage, I'm supposed to take this resistor here and these two are in parallel. This one and this two are in parallel. But since 3 ohms and 7 ohms are in series, I will get the equivalent resistance between 3 ohms and 7 ohms first. And 3 ohms and 7 ohms will give me what? 10 ohms, because they are in what? Series. So 3 ohms plus 7 ohms is what? 10 ohms. And that's the equivalent resistance between 3 ohms and what? 7 ohms. We reduce it again. Finally, I have something that looks like this. Something that looks like this. This is the final reduction. This is 15 ohms. This is 10 ohms. So finally, 15 ohms and 10 ohms are in what? Parallel. So if they are parallel, someone should give me the equivalent resistance. 1 over 10 plus 1 over 15. The equivalent resistance since 10 ohms and 15 ohms are in parallel. Equivalent resistance will be 1 over array equivalent is equal to 1 over 10 plus 1 over 15. Final answer. Array equivalent is what I got an answer? 6. Is it 6? Are you sure? 6 ohms. So I will still draw again to get the final one. Like you keep reducing the circuit till you get the final equivalent resistance. You see how we started from here to here to this to this to this, and we'll draw another one again, the last one. We'll draw another one to show the equivalent resistance. Is it 6? Okay. These 3 volts, and what we got there is 6 ohms. So this is the equivalent resistance of the circuit, 6 ohms. Alright? After, and so this is supposed to come here. Hope you understand. This is supposed to come here. This one I do here is supposed to come because of this calculation. Alright? This is the last equivalent resistance. So, what does it mean? This equivalent resistance, what does it mean? It means that 6 ohms resistor can serve the function of all these resistors here. So instead of putting all these resistors and creating something big like this, we'll just get a 6 ohms resistor and connect it to the power source, and we'll get the same function as every other resistor here. That's what we mean by equivalent resistance. As you solve, you withdraw. As you solve, you withdraw. And you start reducing from where? The end. The side directly opposite to what? Power source. Now let's answer the question. They said the part B of the question says you should get the what? You should get the what? Current. Current across where? R1 and R4. Please listen up. R1. Where is my R1? This R1, isn't it? Now please listen up. When they say you should get the current across a particular resistor, what you're looking for, number 1, is it in series? If it is not in series, if it's in parallel, just look out for if it's in series or parallel and look out for the equivalent resistance. We're looking for the current across R1 and R4. Now I'm going to look at, let's start with R1. R1 is connected in series with what? R2. It means that if I get the equivalent resistance of R1 and R2 give me these 6 ohms, isn't it? If I get the current across these 6 ohms, I have gotten the current across R1 and what? R2. Why? Because R1 and R2 are connected in what? Series. So, to get the current across R1, since R1 is in series with another resistor, you use the equivalent what? Resistance, 6. You're not using this resistance of R1, which is 1 ohm. You're using the equivalent resistance, which is what? 6 ohms. So, from Ohm's law, this is what we're going to take Ohm's law. My school will always enter my mind. We're going to state Ohm's law, and we're going to look at some ohmic and non-ohmic conductors. From Ohm's law, V is equal to IR. I is current, R is resistance, V is what? Voltage. Since I'm looking for the current across R1, I is equal to V over what? R. And what is the voltage? 3 volts. Over this resistance. Is it this 1 ohm or the equivalent resistance? The equivalent resistance. And that is what? 6 ohms. And this is equal to what? 3 over 6 is what? 0. What? 0.5. The unit of current is ampere, capital A. This is the current across R1. 0.5 ampere is the current across what? R1. Please observe, I do not use the resistance of R1. Why? Because R1 and R2 are in what? Series. If I had only R1 here, there was no other resistor, I will use the resistance. If it was only R1 that was here, please listen to me. If it was only R1 that was here, I will use the resistance. But you know I'm not using the resistance because R1 is connected in series with another resistor. So to get the current, if resistors are in series, they have the same what? Current. So just use the equivalent resistance, which is what? 6 ohms. And you are getting the current across R1 and what? R2. 0.5 ampere is flowing through R1. The same 0.5 ampere is flowing through where? R2. Because they are in what? Series. Please, who does not understand? Okay, the part B, they said R1 and which one again? R4. Can you solve R4? The same thing. The current across R4 is V over R. And this is 3 volts over which resistance are we using? Now wait, observe. Which resistance are we using? If you know the answer, please raise your hands. If you know the resistance we are using here to get R4, the current across R4, if you know the resistance we are using, then raise your hands. I want to ask you. Stop doing like this now. Be confident. You know, raise your hands. Okay. Before you know the resistance code, they say we should look for the current across what? R4, which is 11 ohms. Now ask yourself, this 11 ohms, is it connected in series to another resistor? This 11 ohms is connected in series to what? 4 ohms. So we cannot use this 11 ohms as the R, the resistance. Instead, we use the equivalent resistance, which is what? 15. These are simple questions that simple understanding of this particular topic. If you understand this very well, you won't have issues with electrical analysis. Kirchhoff's law. They are using 15 ohms. Why? Because 11 ohms, which is R4, is connected in series with what? 4 ohms. If it was only 11 ohms, we would have used 11 ohms, like what I did here. The reason why you don't use 1 ohm to get the current across R1 is because R1 and R2 are connected in what? Series. Yes, ask.
The resistor for R1, is it not going to series with R2?
Is it not? No, because there is something, just like a wage. There is R3 in between. It is only when this 11 ohms is somewhere here. If this 11 ohms is here, like this, you now say 11 ohms, 1 ohm, and 5 ohms and what? Series. But this terminal cuts it to be in this section, the second section. I don't know if you understand what I'm saying. If 11 ohms was here like this now, you would have like 11 ohm, 1 ohm, and 5 ohm. They are connected by one particular wire, one terminal. Look at, they are connected by one terminal. That's why you can take this, and this as in series. But look at this 11 ohms, look at where it is. There is a wire here that shows you that this 11 ohms is not part of this first section, it's behind. Are you following me? Alright. So it is 3 volts over what? 15 ohms. 3 divided by 15, what do we have? 0. 2 ampere. 0.2 ampere is flowing through R4, isn't it? 0.2 ampere is flowing through R4, which is 11 ohms. The same 0.2 ampere is flowing through each other one again. Which other one again? Which other resistor? 0.2 ampere is flowing through 11 ohms, isn't it? 0.2 ampere current is flowing through 11 ohms. This same 0.2 ampere current is flowing through each other resistor again. 4 ohms because they are in what? Series. Yes, ask.
The 3 ohms and the 7 ohms, I don't speak series with R4.
I do not.
It seems to be
3 ohms and 7 ohms. And they are, see, these 3 ohms and 7 ohms, they are divided resistors in parallel. But since 3 ohms, I can't have another resistor here. If I have another resistor here, this resistor, this one, and this one, and series first. Then when you get the divided resistance, it will not be in parallel with the other one. Understand? Don't get it confused though. If you make a mistake in building the circuit, 3 ohms and 7 ohms are in series. When you get their series connection, their series equivalent, it will not be in parallel. This, the equivalent resistance between 3 and 7 is in parallel because it's connected from one terminal to the other in between. But this one and this one are in what? Series. Ask. Okay, he said, what if you ask to find the current? Okay, look at this now. What if you ask to find the current on R3? Current on R3, listen up. What if I'm asked to find the current on R3? Now, when we look at this R3, this R3 is in what? Parallel. And resistors in parallel have different what? Currents. So I'm going to use this 4 what? Ohms. It is only when there is series that I use the equivalent resistance. If I want to get a current from R3 now, I'm going to be I is equal to V over what? My voltage is what? 3 volts. The resistance of the resistor is in parallel. So since it's in parallel, we use what? 12. But if it's in series, we use the equivalent resistance. Because resistors in parallel have different what? Currents. Alright? You see resistors in series and parallel. If they are in series, the statement from ohms, resistors in series have the same words. For you to make that statement is a condition. Resistors in series have the same currents. Now, I will check out for that resistor, R4. Is it in series or in parallel? If it is in parallel, we will use the resistance. But if it is in series, we use the equivalent what? Resistance. Now, I will check from, I'm not looking at this. See, don't look at this circuit. Your aim is looking at the reduced circuit, not this one. This one is just like a raw data, a raw form, a raw material. These ones are the finished products. So if I want to get the current across 11 ohms, R4, I'm going to look at R4. Look at R4. R4 is here. R4 is in series with what? 4 ohms. This R4, it is you that is looking at it from this aspect. This is the raw data. If you're getting current, you're looking at it from the reduced circuit. Now, what if I ask you, okay, what if I ask you now, what is the current across the circuit? Which resistors are we using? Wait, if I ask you now, what is the current across this whole circuit? Will you tell me 1 plus 5 plus 4 plus this plus this plus that? Which one are you using? 6. Why are we not using this one, this one, this one, this one, this? Why are we using this 6? Because this is the finished what? Product, the finished resistance. So if I have to get the current across this circuit, I'm going to use this what? 6 ohms. What if I'm asked to get the current across and 5? What if I'm asked to get the current across and 5? It's going to be 3 volts over what? What if I'm asked to get the current across and 5? It's going to be what? It's going to be what? 3 over what? 10. Because 3 and 7, this 3 is around 5, and it is in series with what? 7. You check the resistor. If the resistor is series, yes, it is in series, it means you have the same current as the other one. So we are not using their resistance, instead we are using the equivalent what? Resistance. Not 5. Please listen up. If there was no 5 ohms resistor here, which one will I take? If there was no 5 ohms resistor, which one will I take first? 1 and what? Wait, if there was no 5 ohms resistor here, which one are we taking first? 1 and 11 or 1 and 12? 1 and 12 or 1 and 11? 1 and 12. This 11 is on that section. This line is telling you that this is the first part, the first section to take. Look at this 11 is here. This line is telling you that 11 is on this section. It's when I'm done with this right, I can't consider 11. But if this 11 was here, if 11 was here, I will take 11, 1 and 1, 5. Calculate the equivalent resistance. Calculate the equivalent resistance in the circuit below. Calculate the equivalent resistance in the circuit below. Hence, calculate the current across. Hence, calculate the current across I04 resistor. Alright, so let me draw the circuit. So this is it, 7.5 months, 15 minutes. Less than 15 minutes, I'm giving you 10 minutes. What are you using 15 minutes to do? This is 2 ohms. Now this 3.7 ohms and 8 ohms. What type of connection? Series or parallel? Series. When you take them in series, 8 plus 3.7 plus this, what do you have? 13.7. So at the end of the day, I have a circuit that looks like this. 13.7 ohms. If you did not get 13.7, you did it the wrong way.